It seems my system was hacked. Let us see if we can continue. Otherwise, if the hacking continues, then I will try to use another system. So we were here at a recent approach, which is the MOS varactor. It consists of a MOS transistor, NMOS or PMOS, with drain and source connected together. So once you connect drain and source together, then that with this connection with the gate, that act as the diode. So it will be acting, behaving like a diode. This is a new approach or a popular approach. By this, what happens is physically the abrupt change in the capacitance because of inversion of channel, that forms the capacitance. Advantage is it is easily integrated in CMOS. Disadvantage is Q is relatively low in transition region. Because Q is relatively low, so large signal is applied to the varactor in the transition region. This will sweep. This will be swept across each VCO cycle. Then one has to watch out for gate to bulk capacitance also. This shows you what we discussed. The same thing is shown here. You can see that drain and gate are forming the diode, and other regions are shorted out. So source and gate are shorted out, giving you the capacitance. So CGS plus CGD is the capacitance that you will get. Next. Now how to increase the Q, because Q is low, so how to increase the Q for a MOS varactor? What we do here is use capacitances. So you can see what we have done here. We have used capacitance C with a CMOS of W by L. So then capacitance 2C with CMOS 2W by L, capacitance 4C with CMOS 4W by L. So this is the design that you use. Using this design, what happens is you get high Q metal capacitances. These are switched to provide force tuning. So C, 2C, 4C, these are high Q metal capacitances. They are switched to provide you the force tuning. Low Q MOS varactor, which is on the right hand side, the last one. So the low Q MOS varactor, that is used to obtain the fine tuning. So you have force control and you have fine control. For details, you can see this reference by Hegazi and his co-workers. Then if you have studied the push-pull amplifier or class B amplifier, same principle is used in this case where the supply is pulled or pushed. So supply pulling and supply pushing. So supply voltage, that has an impact on the VCO frequency, that we have already seen how it is related. The voltage across the varactor will vary, thereby causing a shift in its capacitance. Voltage across the transistor drain junction will vary, thereby this will cause a shift in its depletion capacitance. So a supply voltage is controlling the capacitance. Since it is controlling the capacitance, therefore the frequency is tuned. This problem is addressed by building a supply regulator specifically for the voltage controlled oscillator. Now, let us look at injection locking in the oscillator. Recall the Barkhausen criteria that we discussed earlier. So what we have is a positive feedback. Instead of a negative feedback, we have a positive feedback. Because of the positive feedback, the oscillation is sustained. The closed loop transfer function for this positive feedback is G, which is y upon x, that you can write as y is the output in the frequency domain, x is the input in the frequency domain. So G is equal to y upon x, that is equal to h upon 1 minus h, and h is the transfer function of the device that we are using. For self-sustaining oscillation at the frequency omega 0, h has to be 1 at omega 0. When you are using frequency omega 0 for self-sustaining, h is to be equal to 1. This is what is Barkhausen criteria. Now, let us look at what is the injection locking mechanism. With the input x is equal to 0, the self-sustaining oscillation will occur at omega 0 because G is equal to infinity. Absolute value of G or mod value of G is equal to, or the amplitude of G is equal to infinity when x is equal to 0, because y by x, G is equal to y upon x. So when x is equal to 0, G has to be infinity. At frequency with small deviation delta omega from omega 0, the magnitude of G will be very large. That you can see here in the figure. On the right hand side figure, you can see at omega 0 it is infinity, the black line, black dashed line, that goes to infinity. G is on the y-axis, so G goes to infinity. If you slightly move away from omega 0, then also it is very high. It is not infinity, but it is extremely high. So what will happen if the input x is a non-zero signal at omega 0 plus delta omega? If that happens, in that case what will happen? If the circuit is purely linear circuit, the output y will contain both oscillation at omega 0 and amplified input at omega 0 plus delta omega. This is because of superposition. So if x is non-zero at omega 0 plus delta omega, then output will contain oscillation at omega 0 and a amplified input at omega 0 plus delta omega. So this is superposition. So if we go to block diagram for the same thing, so we have oscillator, then we take a portion of the output of the oscillator and use a peak detector to detect what is the peak value. So that peak value is given as the to the inverted input of the amplifier, and desired peak value is given as the input of the amplifier, non-inverting input of the amplifier. The output of the amplifier goes to the oscillator to adjust the GM. So this is the circuit. So in real oscillator, the transfer function usually is non-linear. See, it is non-linear to keep the amplitude constant. So either by amplitude feedback as shown here, or by saturating GM characteristic. But let us first look at what happens if the oscillator transfer function is linear and if a small amplitude signal is injected at input x. So in that case, so conceptually this will make the oscillator transfer function linear by letting the output reach a desired amplitude. Suppose the desired amplitude is 1 volt. 1 volt, 2 volt or 0.1 volt, whatever you want. So let us take it as 1 volt, it will be easy to analyze. So undesired output is 1 volt, and disengaging the amplitude feedback, whatever feedback is given, that you take out. So don't give the feedback. So disengaging the amplitude feedback after sampling and holding the GM adjustment voltage at that level, whatever level you get, that 1 volt level. So hold it at 1 volt level. The value of GM is precisely that will make G is equal to infinity. Absolute G is equal to infinity at that point, exactly at that point. It will make value of GM to be infinity. Assuming that there is no drift, so assuming nothing drifts there, the output would be a constant amplitude oscillation at omega 0. Next, let us see what happens if you inject a sinusoidal signal with a small amplitude, say 10 millivolt. So at omega 0 plus delta omega, x is equal to x is a sinusoidal signal with amplitude of 10 millivolt. Then the amplitude G is very large at this frequency. Let us say G is equal to 10,000 at omega is equal to omega 0 plus delta omega. Then the output will be the superposition of 1 volt, which is at omega 0, and 100 volt sinusoid at omega 0 plus delta omega. If the amplitude feedback is re-engaged, which means we have cut off the amplitude feedback, now you provide the amplitude feedback. So if it is re-engaged, it will lower the GM to keep the total amplitude at the desired value of 1 volt. So earlier, now when it was disengaged, it was 1 volt plus 100 volt. Now re-engaging it, we are trying to come back to 1 volt level. So this value of GM would adjust far below what is necessary to sustain the oscillation at omega 0. So only sinusoid at omega 0 plus delta omega will appear at the output with an amplitude of 1 volt. The VCO frequency is hence locked to the input frequency of omega 0 plus delta omega rather than the oscillating at the free running frequency of omega 0. Since it is locked at omega 0 plus delta omega, we call it injection locking. Why you call it injection locking? Because we have injected a sinusoidal voltage slightly away from the omega 0 and we have blocked the frequency to that omega 0 plus delta omega. The injection locking phenomenon, this can be exploited as an alternative to phase loop. Otherwise, the injection locking is troublesome. Example of undesired injection locking. Consider a homodyne system. Instead of a heterodyne system, consider a homodyne system. VCO frequency can be very close to that of the interferers. If the VCO frequency is very close to that of the interferers, so you can see in the figure, on W interferer is very close to omega W0. Omega interferer is very close to omega 0. Red is the interferer, omega 0 is the desired frequency, the narrowband frequency. So that comes from the V in local oscillating local oscillator. So LO signal will contain that. So that will come to the mixture and that will affect actually on the IF frequency. So injection locking, this here it can happen if inadequate isolation from the mixture RF output to LO port is given. Follow the VCO with a buffer stage, in this case with high reverse isolation to alleviate this problem or to avoid this problem. Follow the VCO with a buffer stage. This is a recent technique that is used. You can see there is a this transformer. There is one transformer and there is an inductor. These two are there in the circuit that we use. Then C1, C2 will be as usual in the previous case. So input is given through this the transformer. The input is given through the transformer and the output is taken at the upper M2 output. F in this case is equal to 1 plus gamma by alpha into 1 by 1 plus eta k. The apparent GM boost is the result of the gate and source having 180-degree out of phase waveform. Similar concept, this can be employed in VCOs to lower the phase noise. So what is similar concept here? You can see both the figures. In both the figures, what we have used is the difference principle. So transformer coupling is possible here, but where transformer coupling takes up more area, this can boost GM just by feeding output back to the source. The circuit is different circuit. Then wide tuning range of VCO is available in this circuit. So see these paper, Digest of Technical Papers by David Guermanti. This is a VCO divider and SSB modulator circuit is shown here. And this is another circuit. So these are different circuits only. This is similarly design of the circuit. In these circuits, what we are doing is, instead of using inductor coils, we are using slabs as inductors. That is the difference. Otherwise, it is the same circuit. Diphotophoric. This is not required. Standing wave oscillator. This is what we do here is use a transmission line. So lambda by 4 standing wave oscillator is shown here. Here is a lambda by 4 transmission line. One end is shorted, right end is shorted, left end is you are injecting the energy, so that is oscillating there. Reflective boundaries, what you can do is take two such oscillator lambda by 4 such oscillators, one to the right hand side, one to the left hand side of the injector, and that is what is called reflective boundaries. On the both boundaries, left hand side and right hand side, there the wave gets reflected towards the injector and it oscillates. This is a ring transmission line principle. Same principle, same transmission line, but here you use a ring. Only that is the difference. Otherwise, it is the same principle as the transmission line. So here it is the same ring transmission line. Only thing is, here you get, instead of linear standing wave, here we get the circular standing wave oscillation. Forget this. This is a circuit realization of that ring oscillator that we saw. Next. So with that, we come to the end of VCO. Mixtures we will see in the next class. We'll stop here for today. परीक्षा नोटिस असल्याने
ନାଇଁ 26 ରୁ ଷ୍ଟାର୍ଟ ହଉଛି।
ଆଉ ଗୋଟେ ୱିକ୍ ଆମ ହାତରେ ଅଛି, ସରିବନି ତ ଦେଖିବା। ତମେ ଡାଉନଲୋଡ୍ କରିକି ପଢ଼, ଗୋଟେ କାମ କର, ଡାଉନଲୋଡ୍ କରିଦିଅ, ପଢ଼, ଯଦି ବୁଝି ନହେଲା ମୋତେ ପଚାର। 26 ରୁ ଷ୍ଟାର୍ଟ ହେଲା, ସରିବନି।